I always make my review questions, I include more review questions than there will be test questions, which is to say the exam itself will be shorter, but I made sure that everything that is on the exam is somehow represented on the practice guide. The practice questions are kind of just more separated by topic. Like the exam question might ask 3 different things, and the practice test might be separated into 3 different smaller questions. And this is a note I left your students yesterday that we do have a class. That's not my handwriting. That's way too nice to be my handwriting. That's actually legible. You can't have that. Okay, good morning, everyone. Hope you're all doing well, staying healthy. Let's see. Announcements. I have finished grading all of the in-person labs. So from beginning to end, this is, if you haven't collected them yet, this is every paper lab that has been done. So I do recommend when you get these. These 2 piles are the 2 most recent paper labs. So this is the thermal energy lab where we were dropping metal samples into cups of water. This is the circuit lab we did last week. Was it last week?
Yes, sir.
Okay. So these are the 2 newest ones, but very clearly some people just have not collected their other labs yet. I do recommend grabbing these. If you don't, they're just going to have the recycling bin in a week or 2. Granted,
Oh, we got an 86.
if you come,
We have 86. Not my job. My job is to be.
I always choke on my drink and then food fixes it, but I've got nothing to eat.
Not that one, the last one.
Oh, no. It's okay, we're all good, we're all friends here. Busted.
You have like no 2 or 3 boards, you want 2.
Oh, shoot. Okay. Any virtual labs, I'm finishing up today, so I admit there are probably there are virtual labs I haven't gotten to yet. Grades for those should be coming today or tomorrow at the latest. That is my plan. So that you have the grades and can best make decisions and study based on them as soon as possible. So we're going through those today. Today in class, we do have, we will be reviewing together. We went over went over test 2's exam. I'm mixing too many words and sentences together today. Last time we went over test 2's key, just so that everyone understood what happened on that particular test, what concepts to focus on. Today, unless there's something else specific you guys would rather go over, we can look at the test 1 key, because test 1 stuff will be on the exam, and it'll serve as review and also since most people took test 1 online as well, it'll let everyone know what they need to focus on from test 1, study and remember test 1. And then after that, we can freely discuss anything you guys wish regarding the test, what to study, what to be on it, and maybe work some practice questions together. So, before we get started today, first of all, how you guys doing? It is a very pretty day outside. It's also a very cold day outside. And you know it is cold when I am actually forced to break out long pants and a jacket. trouble is my body can never stay at one consistent temperature, so I'm going to constantly be rolling my sleeves up and rolling them down as my body decides whether or not it is too hot or too cold. Fun fact, I'm not entirely certain of the biology of this, because that is not my major, but I'm under the impression from observation and from being told by my dad that your wrists is one spot where a lot of your blood is going to pass through your wrists to this specific piece here, and then get circulated to the rest of your body. And the distance between your veins and the outside here is just very small, because there's just not a lot of space in your wrist. You can usually see some of your veins and blood vessels in your wrist. Because the skin and the insulation layer is thinner here, you have an easier time of ventilating and regulating your body temperature through your wrists. So if you are very cold, it helps you to cover your wrists to keep your heat in. If you're very hot, expose your wrists, and that will allow you to vent properly. And that's due to thermal conductivity. This is just the spot where the distance between your inside and your outside is very thin. If the distance is thin, the heat travels through quicker. Do I tie that eventually? So, any questions, concerns, issues, comments about anything coming up in the light of coming up in the exam? Anything at all on your minds? Any specific examples or concepts you'd like us to look at today, in addition to the test one? Yes?
Just regarding the exam, like, I know you said the questions would be like a little bit different, like maybe the equation questions, but so much for like just the kind of short answer, but like law of thermodynamics. For the most part, would those kind of be, I mean, okay.
Yes, now specifically about laws of thermodynamics and laws of motion. On my keys, on my practice questions, I always make the practice question list the laws of thermodynamics or list the laws of motion, because I find that's better practice to help you remember them. If you were physically writing them down, physically writing them helps ingrain it into your brain. But on the exam, the question will be changed to look at these statements, number them based on what law they are, like on the last test. So on the exam, there will be one question for, of these, pick the laws of motion, and of these, pick the laws of thermodynamics. I will not mix the two, because that would be a formatting nightmare. There's definitely more written concept questions on the practice guide, just to help remind you of the ins and outs of specific concepts that may be represented on the exam as a formula question. Oh, other announcement. The answer key for the practice questions will be going up shortly, because you need that to be able to check the work. So, things coming out soon, finalizing lab grades, practice questions key. And I'm very sleepy. And hungry. I need to fix those two things soon. You have them, or?
They outside for
Oh yeah, they got it in front of, what's that building called?
They got donuts at
Yeah.
Where?
In front of Neville?
Mm-hmm.
I have to investigate this. Thank you for this information.
They all capping.
I
When
swear
I
I
was
saw,
a student, and
If I go out there, they go, I'm coming for you.
they got coffee and donuts out
I'm
there.
looking for you now.
if I
You
don't
can
get
look,
coffee,
bring
can I
me
get
donuts.
twice as many donuts?
Huh?
If I don't get coffee, can I get twice as many donuts?
Probably so, they're probably just.
That's a question I can't answer.
So you mean to tell?
Because coffee wasn't even on that.
Cause they like to stack, or they have like a.
They have boxes of Krispy Kreme out there.
Like they
How
just.
impressed do I get to take a whole box?
I just know
They're
that
not giving me no answers.
I'm doing the best I can.
Donut inquiry is very important.
Where's the nearest Krispy Kreme?
I need quantity, not quality. I want
Landon told me last night they had 12
Sounds
boxes
like
of
what you want is a
Krispy
box
Kreme.
of donut rolls.
quantity. Tom, they only got a box,
12 boxes.
so they only got 12 boxes.
Only?
Only 12 boxes?
12 boxes, and they're probably dozen boxes each, so.
That's
Yeah.
responsible.
Those donuts go.
144.
Oh, yeah, it was like,
No, go. They go, I'm sorry.
It depends on how many people know about it.
Come back later. They're like, it's in front of me.
You could go now.
Well, when I was a student, both the campus and also the church down the road would work together to put like a cookie stand where you would go into Springs and volunteers from the church would just say, hello, here's free cookies and maybe some soda. Good luck with studying. Also go pet this dog.
We get enough.
They would bring in therapy dogs to help during exam study.
We get enough cookies and GDA's on donuts.
If you go to get it, then you know, please.
Cookies from PH pretty good.
Yeah.
Any other questions, concerns, comments?
I bet they're lying like a Chick-fil-A line too. That's how I'm gonna wrap around.
Dude, the Chick-fil-A in, what's it called?
Lawrence.
Lawrence is never packed.
Yeah, there's never
That's because it's Lawrence.
Yeah.
The most packed place I've ever seen in Lawrence is Walmart.
Yeah.
I never seen that. I never saw it.
Word of advice, because the scanner upstairs tends to scan things sideways, it defaults to landscape mode. When you pull up the keys on the website, if you go into this tab here, the little double arrows that says Tools, and open that up, the rotate function is hidden in there. Now I'm actually going to re-download this because I don't know where the old file is, so I'm just going to re-download my old file.
We can go over the movies equation, like how you cancel out things.
Yes, sure. Is it-
That thing.
That is hands down the trickiest formula that we've covered. And it's the one that is usually designed as this is the hard question that's worth like 10 extra points. That's by design. It is okay if you don't always get that question completely right. That's why the bonus points are there. I want to definitely go over this, and then we can specifically look at Bernoulli's as a very good question. Thank you. One last swig to stay hydrated. As the air dries out, remember to keep drinking water. So, this is good old-fashioned test 1. Question 1 on test 1. If you have your test available, I do recommend pulling it out to look at it. Question 1 was simply, how do you find force of gravity? There's actually 2 answers that I would have accepted, that I did accept when I was originally grading this. The 2 answers in general are, 1, you can find the weight of an object on planet Earth by multiplying its mass times 9.81. But the answer to find gravity anywhere is with the big universal law of gravitation formula. These are both acceptable ways to find gravity in specific circumstances. This one only works on a planet. This one is more general. The one answer that's definitely not acceptable is if you just say mass. Mass and the force of gravity are different things. Make sure you remember that one. Excuse me. Question 2. This is displacement in 2 different directions. You've got a hiker that's going all which way. It's up to you to make sure that you only add together the vertical components and that you only add together the horizontal components. I have done those 2 pieces of math separately. I know my handwriting is terrible and the screen is blurry, so I will read this out to you. For the x-axis, we've got 20 east, 32 west, and then 3 east. Keep in mind, east and west are separate directions in the same axis, so if one of them is positive, the other would have to be negative. I will be considering east to be positive, simply because on our coordinate system, when you usually draw out x and y, usually to the right is positive and up is positive. If you make west and south, negative. So, only adding together the horizontal components, 20 minus 32 plus 3, gives us 9 meters west. And the vertical axis, or vertical components, are 30 meters north, 8 meters south, and 15 meters north. Add those together, make sure south is negative and north is positive, and that'll give you 37 meters north. Make sure to track your units, and if you wanted to, if someone, I had several people go kind of a step beyond and do the Pythagorean theorem to figure out like the actual straight line distance, which is more than what I asked. This is acceptable because in the class itself we didn't actually do much in the way of that sort of trigonometry. So if I, in a question like this, find the resulting displacement, this is an accurate way of saying it because they didn't know axes. So this hiker's displacement is mostly north and a little bit west. So they went in this direction. Important exam concepts to remember from this are, in two-dimensional problems, make sure you look at each dimension separately. Question 3. This one ties together a couple different topics about force. We're examining a sled being pulled by a person. It's being pulled horizontally, the force is horizontal. And the sled is sliding at constant velocity. So question 1 asks, what is the net force on this sled? If it is being pulled at constant velocity, that means it is not accelerating. If something is not accelerating, the net force is 0. Doesn't matter what the other forces on it are, if it's not accelerating, they have to add up to 0. Part B, what are all the forces on the sled? What I was looking for here is a list of the forces acting on this object. There are at least 4 of them, 4 that I was looking for. There's the force from the person pulling forwards. Friction would exist pulling it backwards. Gravity would exist pulling it down. Normal force would exist pushing it up. All of these things work together to add up to 0 to keep the sled from accelerating. So part B, you didn't necessarily need to put a drawing, but you did need to at least name them. And part C, you were just to tell me what all these forces were themselves equal to. So you take your 4 forces and you assign a number to them. We already know the force forwards is 100, because the problem told us that. And since things have to add up to 0, and since force forwards and friction are opposing each other in the same axis, the force of friction must add up with the force forwards to create a force of 0. So friction would have to be 100 in the opposite direction. When you pull something at constant speed, your force forwards is equal to the force of friction backwards, which is why when you turn on cruise control in your car, the engine is programmed to exert just enough force forwards to counteract all the forces slowing you down. Next, this box is not accelerating up or down. It might be moving to the right, but it is at least not being pushed upwards or falling down at the same time. That means that normal force and gravity must be equal to one another. You can find the force of gravity because we know the mass of the sled. Normal force must be the same magnitude, but upwards. 20 times 9.8, yes. Any questions on page 1? Okay. Oh, things to definitely remember for your test here. Specifically, if something's moving at constant velocity, the net force on it is 0. Forces acting on an object cancel out when the net force equals 0. Be familiar with all of these different types of forces. They will show up. Next, part 4. This is a projectile motion question, which is inherently a motion in 2 directions question as well. All of our projectile motion questions are going to look pretty similarly. Some object is going to be fired horizontally from the top of something tall, a building, a cliff. Occasionally we might drop something off a plane. So The setup will always look pretty similarly. You can usually represent it with this exact picture. Thing moving horizontally some height above the floor, and usually your task is to figure out how far from the edge of the cliff something will land. Sometimes I might reverse this. You might know how far away from the cliff it lands and be asked to find its horizontal launch speed. The same method will get you to that answer. It's not that different a question. The main thing to remember for these types of questions is, again, you have to look at each axis separately. When deciphering my answer keys, the circled numbers tell you how many points you get for each thing. Simply by writing the correct formula, which is the delta D equals velocity initial times time plus 1/2 acceleration times time squared formula, simply writing that down gets you points. You then get a further 3 points by recognizing you have to do that formula twice, once for each axis. So that's 7 points before you even plug in a number. And that's basically half the question right there. Again, we have to look at each axis separately. And in these types of questions, the vertical axis always determines how long you're in the air. When you are launched horizontally, in terms of gravity, there's no difference between that and falling, because there's no initial vertical velocity. So when we look at our formula, there's no initial vertical velocity, so this piece cancels out. You got 2 points just for crossing it out. And we're accelerating due to gravity. We plug gravity in. That's supposed to be negative 9.8. But my nines look like ones on the best of days. They really look like ones oriented zoomed out. But you plug in your vertical components and you determine the hang time, the time in the air, which should be about 2.5 seconds. Now that you know time in the air, you can take that number and look at the horizontal axis. The horizontal axis is what is ultimately going to determine how far we can go in that time allotted. So, looking at a horizontal version of our distance formula, we do have some horizontal initial launch speed, but we're not accelerating horizontally because gravity exists in the vertical axis. If you are a projectile, gravity is the only thing making you accelerate. There will be no x acceleration. You get 2 points just for canceling that part of the formula out. Then you can plug in your velocity and your time and solve for distance. This is supposed to say 61.86. My apologies. Things to remember here. The basic structure of a projectile motion question. Examine each axis separately. Remember which formula you want to use. Again, that's going to be delta D equals V initial times time plus 1/2 a t squared. This is the third formula we learned on that list of fantastic 4 equations. If hypothetically you were given how far away from the cliff the ball landed, and you were asked to calculate its initial launch speed, the only thing that differs in that scenario is this last step. Because instead, you wouldn't know velocity, but you would know delta x. So you plug in the number you know for delta x, and you solve for velocity instead. The only difference there is that last piece. Cool. Okay.
In that first one, did that t have to use square root because t is squared, isn't it?
Correct. This is after taking the square root. Because 30 divided by 1/2 would be 60. 60 divided by 9.8 would be 6. Square root of 6 is about 2.5. Next, number 5. This is a rotation question. So, concepts to remember here. Basics of the rotational formulas. put my marker in my own pocket, and then I wonder where it went. I must have the object permanence of a baby or a T-Rex. Maybe even a baby T-Rex. Okay, no, rather than writing this, it'd be a lot faster if I just find the formula sheet in there. Okay, so tabbing away for a second. As a refresher, these are our linear motion formulas. These formulas should help you work out the math for anything involving regular linear motion, except displacement, velocity, acceleration, and time. They are related and connected to their angular counterparts. So these formulas here are the angular versions of the linear formulas. They work exactly the same, you just swap things out for their angular component. And these formulas let you convert the angular to linear of the same type. The radius of the spinning object is the conversion factor. For this particular question that we were just looking at, understanding those formulas and being able to do the conversion between angular and linear is the main takeaway here, and things that will come up on the exam. So, we are given a merry-go-round that is spinning. We do know its initial speed, its angular speed, but we are given it in rotations per minute. All of our formulas are designed to accept radians per second. So the first thing you do is you get points for converting rotations per minute into radians per second. A rotation and a radian are basically two different ways of describing the same thing. It's just a question of angles versus whole rotations.
How do you convert the two in between?
Good question. The conversion is one full rotation, which I will usually abbreviate to ROT, is equal to 2 pi radians. That is how many radians are in a full rotation, which is also the same thing with the Elton brain as 360 degrees. All of these three things mean exactly the same thing. But our metric formulas are designed for radians. Because that's naturally what, if you multiply by the radius, you'll get like diameter, distance, etc. Once you've done that conversion, and you'll have to convert minutes to seconds as well, you can take that information, and the first thing we're asked is, what is the linear velocity of each child? They're on the same wheel, so they'll have the same angular velocity. So you take that over here to our linear to angular conversion and find the linear counterpart to each of their speeds. Their radius does determine this. Each child is at a different radius from the center. Part B, what is the centripetal acceleration of each child? That is admittedly a different formula. Centripetal force and acceleration is kind of like an in-between between angular and linear, because it's a linear force that makes things spin. So the formula for centripetal acceleration is AC equals v squared over r, or you could alternatively use AC equals omega squared times r. Both are valid, it just depends on if you know the angular or the linear. We know the angular and the linear, so dealer's choice which version you use. On my key, I think I went with the angular version. So AC equals angular squared times r. Do that, and you can find the centripetal accelerations. This is technically a linear force, which is why the units are in meters per second squared, because it points in a straight line to the center of the orbit. It's not itself rotational or pointing in a specific axis of rotation. It's pointing in a straight line. And then part C, find the angular acceleration of each child. The trick here is merry-go-rounds in operation are operating at constant velocity. if velocity is constant, there's by definition no acceleration. There's this acceleration because this is just changing its direction, not its speed. Its angular velocity is not changing with time, which means its angular acceleration is 0. Does that make sense? Does that not make sense to anybody? Okay. Again, be familiar with the angular versus linear counterparts, how to compare between them, how to work each one, and also the formula for centripetal acceleration. Moving on, number 6. This is a work question, the physics concept of work. Person is exerting a force in order to walk forward. The wind is exerting a force trying to push them backwards in the same axis. First two things you're asked is, what is the work done by the wind? So you multiply the force of the wind times the distance the person walks in the same axis. Second question is, what is the work of the person? So that's the force the person exerted times the distance they walked. We've got two different numbers here. The wind's work is negative on account of the fact that it's in the opposite direction of motion. It's trying to take energy away from this person. Walk forwards, the force is backwards. One of those numbers has to be negative. Now, part C. What is the total net amount of work done on the person? The person did this much work. The wind did this much work on them. So this is the work outside of the person that is affecting them. Therefore, the same number is the work done upon the person. It's different to the work done by the person. And the last question, what is the power output of the person? A couple different equations for power come up this year. For this question, power is equal to work over time. It's the rate at which energy is used. This is the total energy the person utilized. This is the amount of work that they did in 2 minutes. So this is what you would plug in for their work done, divided by time, which is going to be 2 times 60 to convert 2 minutes into seconds. And that'll give us a power output of 20 watts. So this person's effort could power a very low energy light bulb. Is that not what I said? Sorry, 25 watts. Time for a water break. Pardon me. Things to remember, the work formula, the power formula, that you can do negative work if the force and the direction of movement are in opposite directions but the same axis, etc. Number 7, this question is about converting GPE into KE. As you drop an object, the amount of energy it has stored in its height will convert into kinetic energy. So initially, you can find how much kinetic energy this object has using the kinetic, you can find how much gravitational potential energy this object has by using that formula. Part B, the thing to remember there is, as an object begins falling, its GPE will naturally convert into KE as its height decreases and its velocity increases. So the moment before something strikes the ground, the moment it's like at a height of 0, but it hasn't actually touched the floor yet, at that exact moment, all of its GPE will have become KE, and it's moving at its maximum speed before it actually goes splat. So the same number that you just found now becomes KE. The same thing happens in reverse if you throw something upwards and pause time when it's at its maximum height. Once you know this is going to be the final KE, we're using that energy formula to find its velocity right before it goes splat. This is the maximum speed at which it would strike the floor. Things to remember here. Converting between energy types, the sort of relationship between KE and GPE, and how to utilize the formulas. Number 8, this is a torque question. This is the only torque formula that's going to be on the exam. We did talk about one other one, but this is the one that you'll be graded on being able to use. Torque is equal to radius times force. Things to remember here: one, how to use that formula. Two, the fact that if you want to balance a seesaw, the torque on one side needs to equal the torque on the other. So, first thing, a child is going to sit 2 meters away from the fulcrum of a seesaw. The force they're going to exert is equal to their weight, so mass times 9.8. That will give you the torque that they will exert on the seesaw. On the opposite side, another kid is going to sit, and in order for them to balance out, they have to sit at a certain radius, exerting their weight. So you want to plug in kid 2's mass instead, but they need to exert the same amount of torque. You get the same torque as before, plug in the new mass, solve for the new radius. Because this kid has more mass, they're going to need to sit closer to the fulcrum to make sure they're not exerting too much torque. Next, number 9. This is a collisions question. Now, on test 1, you were only asked to do an inelastic collision. You do need to understand what happens in an elastic collision as well. So, this is your inelastic example. Make sure you look at, say, your homeworks, your notes, the test 1 study guide, to make sure you understand how an elastic collision would also work. Main things to remember about all collisions is that total momentum will be conserved. So you find total momentum of each object before and afterwards. And in an inelastic collision, this is the only thing conserved. Two objects stick together, they have the same final velocity. You will find the speed at which they are now traveling together, joined as one. Again, this is distinct from an elastic collision where things tend to bounce off of each other and be moving at different final velocities. So elastic collisions are the harder ones to work.
That's the formula we use with the mass times velocity initial plus mass.
Right, so
mass initial times velocity initial plus mass 2 initial times velocity initial, something like that.
almost. Wait, say again?
It's like mass 1 initial times velocity initial plus mass 2 initial times velocity initial equals mass 2 final time plus, mass 2 final time velocity final plus mass 2 final velocity.
Yes, so what we've got here is momentum equals mass times velocity, and we're just doing that multiple times, once for each object before and once for each object after. Very good. Remember, an elastic collision is slightly different and somewhat harder because kinetic energy is also conserved in an elastic collision. So elastically, you have 2 other starting points you can use. These 2 starting points are valid for elastic collisions in a single dimension only. These don't work for inelastic ones. But these are at your disposal for elastic questions. And the last question, this was definitely the hardest one of test 1. So this was the test 1 equivalent of Bernoulli's. This question is about the intersection of the big force of gravity with centripetal force, because in space, when one object orbits another object because of gravity, gravity would act as a centripetal force. So you know the mass of the meteor and the planet, you know the speed at which the meteor is moving around the Earth. You're ultimately asked to figure out how far from the center of the Earth the meteor will orbit, its orbital radius from itself to Earth's core. Most of your, a decent chunk of your points are awarded just for listing these formulas. So listing each one separately gets you a total of 8 points. You then get 10 points for knowing to set them equal to one another. These two, in this specific case, gravity is acting as the centripetal force, so we can set these two formulas equal to each other, and then a few things start canceling out, making our life easier. If M1 is the meteor's mass in both cases, then that'll cancel on both sides. You don't even really need to know the meteor's mass to be able to do this. Also, one of the radii will cancel on each side. They're both underneath, so that'll simplify down to v squared equals g times Earth mass over orbital radius. Simplify to solve for radius, and you will get nearly 1 million meters, which is a lot. But that's only about 1,000 kilometers. I'm pretty sure the space station actually orbits higher than that. The space station is not actually very high up. I know it's in space, but it's actually in low orbit. There's a certain spot on planet Earth, like if somewhere between the bottom of South America as you're going to the Antarctic, there's a certain point in the ocean on planet Earth where you are so far away from every landmass that the closest humans to you is the space station if it's directly overhead. There's a certain point on Earth where it's closer to go straight up to the space station than it is to turn around and go back to South America or forward to Antarctica.
Because that's about like 620 miles.
Correct, yes.
So like, you gotta be pretty far.
You can
Road
you
trip.
can go on a road trip to the space station.
Road trip.
At a certain point, that's not a road trip anymore.
It's a road trip to Florida, man. The magic school bus, that's it.
Magic school bus.
They go anywhere like that.
I always wanted a magic school bus when I was a kid, and most of my Lego creations were just, this is my school bus, and now I'm going to turn it into a rocket. This is when I was 6. I was first. Miss Frizzle and early Bill Nye episodes turned me into a scientist.
I used to play that at elementary school. I would get all this.
Bill Nye is still useful when I was teaching high school. It's just, the episodes are well made and accurate. Magic School Bus 2, actually. Okay, so that's test 1. I do recommend looking at it for good study material. The key is on the website. Any questions about test 1 before we begin a cursory analysis of Newton's equation? Okay, so let me put that equation up on the board. That'll be the last thing we do today. One of the nice things about this, unfortunately, long equation is the fact that it is symmetrical. Which means as long as you can write one side, you can write the other side. just swap out all the ones for twos. Again, everything on one side is mirrored on the other, so even though it is long, it is at least symmetrical. And this formula exists to compare every aspect of pressure in different parts of a system. Within the same system, fluids can be moving at different speeds within the same system. They can be exposed to different amounts of pressure in different parts of a system. They can be at different heights within the same storage tank, and that will affect what is happening at that particular spot. This is sort of a before and after comparing two different pieces together equation. And the good news is, any question I asked you, at least two or more elements of this particular question are going to cancel out on one side or the other. As an example, the closest example that I actually have to hand is probably the practice test. So let's find the Bernoulli's question over here. Okay. So on the last page, the second to last question on the practice questions is the Bernoulli's equation question here. And this is probably one of the simplest versions I've ever actually given you. It's also a surprisingly short question. The question itself doesn't give you a lot of information, but that is to help things start canceling out. A high-pressure water tank springs a leak. If the water ejects from the pipe at a speed of 32 meters per second, what is the water pressure inside the pipe? So we are comparing two different parts of the system. There is the part outside the system where water is ejecting at 32 meters per second. That's going to be our after. Our initial is inside the tank where the water is not moving, but under some amount of pressure. So this is going to be our inside. Really, you can list either side. It doesn't really matter which side, left or right, you can make the inside or the outside. My brain just goes left to right. So inside the tank, there's some total amount of pressure. Water's not moving yet, and we're not informed of any sort of height. The pressure just exists inside of this system. So this term is can encapsulate the pressure inside of the tank. And therefore, these two terms can both fall away to zero since it's not moving in the tank, and this term is already factoring in every single piece of the pressure that's not being caused by any amount of height. So this term can fall away to zero. So that's two things canceled on the left side. On the right side, the pressure inside the tank no longer exists. We are now moving at some velocity, but there's still no height of water above us. So tank pressure is gone. That's no longer a factor. There's still no fluid height above, there's no height of water above us. So we can cancel those two terms on either side. That should leave us with pressure inside the tank is equal to density times velocity squared over 2. We are solving for P1. Density of water is 1,000. We're ejecting at how fast? 32 meters per second is very quick. If you were running at that speed, you could cover a football field in 1 second. This is why high pressure pipes are dangerous and why in cartoons, when they sprung a leak, typically the rivets would rocket off of them at very high speeds. That actually happens in real life. pressure pipes are not to be trifled with. And divide by 2, and actually tell you the pressure inside of the tank is separate from the air pressure around the tank.
Cheat sheet.
And that should be approximately one pretty big number.
512,000.
That sounds right. I don't have it worked in front of me. Let me fish out tiny. Square, 500,000 divided by 2. Yep, 512,000. That is at least 4 times greater than atmospheric pressure. You would feel that. That would make your ears, no, your ears would do more than pop. They would pop inwards and stay there. Cool. Pressure is no joke. All right, thank you all. Tomorrow will be more review, so come prepared with study questions. If you feel you don't need the review, then you do not have to attend, but I will be here answering any questions you have. And I do hope you all have a wonderful day. Thank you very much.
I'm going to see, man, I got on the job.
It's not trying to make fire. Is that what you've been trying to do?
No, it's just smoking up a lot, that's all.
Okay, it will still do that. Actually, if you put a little water in there instead of fluff, it will steam up instead. I'm gonna be honest. That smoke, some of it is smoke, but some of it is also steam. Because in addition to adding in a lot of heat that's heating up the fluff, you're also compressing the water vapor present inside the tube, and you're forcing it to compress back into more visible water. Finals are never very fun.
No, my Spanish is fine. No, I say my Spanish is fine. It's not like that. It's not like that.